the -3 halves, there's your point of inflection. I'll put a point. Isn't that cool? And there's a point of inflection on that curve at that point. Nice. I love it. And when I want you to see how this could, but do you understand that you do this at home, I knew this could bug you, right? The product, plus you look in the back of the book, you'd be like, most of the questions, Connor, on how did they what? Move that up here. The little things, you know, just the little algebra things. And I also wanted you to see that, my gosh, if you eliminate the parameter, you might find this just easy to deal with. I'm sure you did problems like this in Calc 1.
So if we do it like that on the test, is that alright?
That's totally fine. That's totally fine. Now, I know the book sometimes says, do it both ways. It's just me, I'm not going to ask that.
Okay.
Like, in this problem, they just said find it. So you're like, hey, I'm following the directions. Now, let me read it again. Isaac, they wrote this. Find dy dx and find d squared y dx squared.
Okay.
And that's all they wrote. And they're like, okay, I'll do it. I'll eliminate the parameter and then go from there.
Okay.
Hey, I did look in the solutions manual. I was curious. And they took this route.
Okay.
They didn't even mention that, you know?
Alright.
I love it. Hey, can I raise? Great questions. And I do love how you were highlighting earlier about the domain. Some of these you look and you go, whoa, 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 natural logs. Right? Like we're noticing here, Edwin, can x be negative? Never. Can x be 0? See, what's that domain? In terms of x, talking about domain, if we're talking about x, we're like x has to be higher than 0. But this had t's in it. Remember, like, but for key values, t could be negative or positive. That's what I want you to see here. Sometimes it can be confusing, but we're talking about the same curve. Some things are easier to find parametrically, some things are easier to find by eliminating the parameter. But Calc 3, you start doing these cool line integrals and surface integrals, we're going to want to get everything parametric. Especially because everything's going to be three-dimensional. Right? And then Kate, I'll go back to it. You'll look at lines in 3D space and you'll be like, oh, it'll be stuff like this. 2 minus t y equals 5 plus 2t. And z equals 8t. That'll be a line. It'll just be in three-dimensional space. It'll be in three-dimensional space. I think you're going to love Calc 3. Because everyone, do you recall what that made?
Circle.
That made a circle. So I want to see how good you are. You go take Calc 3, and you just add this. So now the z, everyone think the z-axis is just going straight up through this roof here.
So it'd be a sphere.
So if you got a circle, but t just keeps increasing, what's this curve going to do? That's a curve.
Cylinder?
Oh yeah, I heard it. It's like a spiral. So this, don't worry, this is Calc 3. I can make a bonus though, right? This would be a spiral. Do you see what's happening? What's going on in this relationship? It's circling, but what's this doing? As t increases, z what? Keeps getting higher and higher. It makes a curve that, I mean, you've seen things like this, right? Like a corkscrew, like a helix. Isn't that cool? You'll love Calc 3. Blast. That's all they're doing.
What would make that a sphere?
A sphere. So when you talk about 3, now we're talking about, we can go Cartesian first. All right? But just because your question, this is, I'm going to start here. That's a circle, right? That's a circle in three-dimensional space. So what I'll do is, what's distance for them? Because this will only take everyone 1 minute. He's got a neat question. What was the distance for them? Used to what, like, if I do distance from origin, x plus y squared, we take this curve root, Pythagorean theorem. But if you had a z component, right? Now you can talk about not just a circle from the origin, but you could think like three-dimensionally, like everything at distance what? Here's your point, and go a same distance away from this point, you'll form a sphere. So all I'm going to do is add this. I just want you to square both sides. You'll come up with the equation of a sphere. Like square that, and we'll call it the radius. Let's say it was what? The radius was 2. So here's a good example of a sphere. X squared plus y squared plus z squared equal to 1 is a sphere. Now I know it's in Cartesian. It's in Cartesian right now. But when you talk about spheres and you want to look at those parametrically, that's a whole other story, right? But we're just talking about curves. See the difference? Curve versus, that's actually a surface. But I wanted to see that it's not far off from what we're doing now. That's the equation of a sphere in three-dimensional space, with a radius of 1. What would be the radius of this? You probably know. A sphere standing at the origin with a radius of 5. You'll love Calc 3. But there's two things going on in Calc 3. You got surfaces. Everyone like a rooftop or that ceiling. You got surfaces, or here a surface, like a plane. But then you have curves still, right? You got things like things traveling through space like this, like asteroids and stuff. Hey, cool. Hey, we're now going to do polar coordinates. Has anybody ever seen that before? Sometimes students have seen this in a pre-calc course. It doesn't make it into all pre-calc courses though. Well, once again, here's another topic, everyone, that's essential for Calc 3. So it may seem a little bizarre because we're going to hit this section today. Tomorrow we'll talk about area in polar coordinates. We'll draw some polar curves and find area. Okay. But again, it's essential for Calc 3. But we hit it now and then we move on in chapter 11. We finish up this course with series. So again, it seems like a section like, why did we do that? It's for your next course, going into calculus. So polar coordinates. Everything we've been doing so far has been in Cartesian coordinates, right? I mean, we just dealt with a parameter t, but we're still talking about x and y in terms of Cartesian. So can we look at things in polar coordinates? Sure. The coordinates will be a radius and a theta. Just those two. Remember x comma y? R comma theta. R, we're going to talk about that's the distance away from the origin. And by the way, we got a new name for the origin. You might like it better. One syllable, pole. Polar coordinates, let's call that the pole. P-O-L-E. Right? That's the pole, but you could still call it the origin. Gives me a distance away from here. I do want to be careful when I say the word distance. R can take on a negative value. I'll explain that before you leave today. Okay? R can be negative. Second thing is theta is the angle, just like in trigonometry, that when it's positive, it rotates which way? Counterclockwise, and when it's negative, it rotates clockwise. So all we need is conversions. So let's draw a triangle. You'll find this easy to remember. On a test, final exam, Calc 3. And let's find the conversions from x's and y's to r's and thetas. So I do this as the x-axis, this is the y-axis. Where's the radius? There's r. Where's theta? Right there. Theta is the angle, I'm going to move it this way. Or, what can I call this line? X. What can I call this line? Y. And can you do a little SOHCAHTOA for me? And tell me what x equals, and we'll have the conversion. It'll be easy to remember. I'm telling you, on a test, you just draw that picture. You gotta forget the conversions from polar coordinates to Cartesian. Make that triangle, and you'll figure it out. What's cosine of theta? Adjacent over hypotenuse. Cosine of theta is x over r, so what does x equal? R cosine theta, got it. That's x, that's a conversion. From Cartesian to polar. What would y equal though? Let's see. Well, I noticed sine of theta, I'm doing SOHCAHTOA. Sine of theta is y over r. So does y equal? R times sine of theta. Isn't this cool? Just remember, just make that triangle, do a little SOHCAHTOA, you'll know these. Now, can someone we should put it down. An equation with the Pythagorean theorem. Yeah, do it. What is it? X squared plus y squared equals? I'm going to write it. There we go. Okay, I want us to make one more equation though. You got to help me out. What's an equation for theta? If we want to get theta so we can convert it, what would theta equal? Well, I noticed like, hey, when tangent of theta is y over x.
Cosine inverse?
Yeah, there you go. And I think I'll do inverse tan. I'll do inverse tan. So theta equals inverse tan of y over x. That's all we need. I'll put it right here. Everyone will figure out theta. It's inverse tangent of y over x. The only reason I chose inverse tan there, Armando, is because a lot of times they're going to give you a point like an xy coordinate. And you're like, oh, I'll just use the y and x there. The cosine would deal with the r. There they are. These are the conversions. So here's my first problem. Okay, the angle is 4. Power 6. Now this is a point in polar coordinates. This is a point in polar coordinates. Can you help me figure out where it is? What quadrant is that in? So what happened? It went a distance of 4 away from the origin or the pole. But which way did it rotate? That way or this way? It rotated that way. What's power 6 as an angle? About 30 what? 30 degrees. So when we rotated 30 degrees and went a distance of 4 from the pole. So to get an idea, where is this point? Rotated from here, 30 degrees, but how far from the pole am I now?
4.
So I'm going to plot, stop there, right? Does that make sense? Cool. Now I want to play around with this. What about this point? Bless you.
Excuse me.
And this is R, this is theta, this is R, this is theta. And I want to talk about this point. R can be negative. It's real simple though.
Should be third
So
quadrant.
just to get it straight, these points are based on the angles?
That's right. You could start rotating first. And we're standard position. We always rotate from standard position. Just like in trigonometry, you're right there. And if its angle's negative though, which way do you rotate? That way. I'll throw one of this at you. You're like, what about a 4 negative power 6? You're like, okay. Rotate that angle. So all polar coordinates is based off angle rotation and distance away from a pole. The first thing I want to talk about though, Kate, is R can be negative. So what is this defined to be? When it's negative, I heard someone knew. What quadrant was it in? He knows in what third quadrant. He's seen this before. When R is negative, what you do is you just go from this point right here, draw a straight line to the origin or the pole, and go to the opposite quadrant, and it'll be the same distance away from the pole. So where would this point be roughly? So when here's 4, power 6, I just do what? Go down here, straight through the line, and do what about here? That make sense? You know see what that point is? That's how you think of it. Think where 4 pi over 6 is first, then take a straight line right to the origin and go to the opposite quadrant. It'll be the same distance away from the pole. I know it's a little weird, but R can be negative. Right? So I know I'm using the word distance, but by this definition, R is allowed to be negative. That's how it's defined to be. Does that make sense? Now, hey, one more. I'm going to change the number. I'll use a different angle. How about 2, but negative power 3? Kate, where would that be? Which quadrant? You could do the angle first though and rotate 60 degrees, and how far away from the pole would it be? 2. So about 2 away. You know I'm estimating because I got to go 2 notches. I can't make the tick marks. My colleague, one of our Professor Ealer, he always passed out polar paper on this deck. Okay, yeah, polar paper. It's got all these circles, so you can actually count the what? The 1, the 2. It's got all those circles. So you can hate me for not passing out the polar paper. The only reason I don't pass it out, you don't have polar paper during a test, do you? So I'm like, I'm not going to give it to them. I don't want they think they always have these polar documents. All it is a bunch of circles, right? Because that's all we're doing is rotating.
And the test on polar paper.
On polar paper. Yeah. Hey, I'm going to have a fun game. And when you see this point, I'm going to throw a bunch of more points down. I want you to tell me which one isn't the same as this. Okay? Which point is not the same as, what's that, it's 4 or what? 4 pi over 6. Which point is not the same? Okay. There's one. This will be fun. 4, 13 pi over 6. 4, make 11 pi over 6. What else do I got there? I've got negative 4, 7 pi over 6. I get 4 negative 7 pi over 6. Okay. And I actually came up with another thing. Negative 4, negative 5 pi over 6. Take your time on this though. Which point is not the same point? Is not the same as the point 4 pi over 6. And where's 4 pi over 6 again? I'm gonna plot it. Which quadrant? First, it's about 30 degrees rotated, but a distance of 4 from the pole, right? And we'll just go through here.
Should be the fourth, right? Yeah.
What's that?
Should be the fourth one. Yeah. Negative 5 or 6. Or I'm sorry, negative 7.
Dave was just flying through these. He's checking them all. Where's this? Because it went 13 pi over 6.
Right.
Did a full loop and then
Right.
came back here. That's the same, right? Right, you're the same. Does anyone realize that? It went, just rotated all the way around, full loop. Go terminal angle, right? That's the same. How about this one though? And when it rotates negative angle, which way does it rotate? It goes this way. So it went to negative 11 pi over 6. So all the way around here, still a distance of what? 4 from the pole. You're the same. I mean the same point. You're the same point. How about this one? Now be careful, that's a negative r. So rotated. Where's 7 pi over 6? 6 pi over 6 would be right here, pi. 7 pi over 6 would be right here. But then r is negative, so what happens? Going the opposite quadrant, right through that origin, where do I go? Back to there, that's the same. So Dave, very good, where's this? He said something's up with this guy.
Should be.
I go 4 away from the pole, but I rotated negative 7 pi over 6. I rotated
60, bro.
quadrant 2.
That's,
Someone see that? You're not the same. You're not the same. Now how about this guy? Where's this? Let's start with that. Let's rotate negative 5 over 6. Where's that? I always like to do the angle first. Just rotate, rotate, rotate. Negative 5 over 6 puts me here, right? But the r is negative, where would I go? Same point. All these are the same except for who? Yeah, you're the one that's different. Awesome.
Why is negative 4, 7 pi over 6 not in the third quadrant? 'Cause I'm trying to see, I was thinking if it was negative 4.
4, 7 pi over 6 would be. So you rotate third quadrant here, but r is negative, so now you gotta go over here. Let me do it again. That point is here. That's 4, 7 pi over 6. When this is negative on r, that means, by definition, go straight to the origin. The point will be on the opposite quadrant, same distance away. It goes right there. Okay. Cool. Is that all right with that? Hey, now we'll do equations. Great job with points. Oh, and before I do equations, I was just thinking, hey, we should take one point and convert it the other way. What is that point in Cartesian? I'm just curious. Can you get me back to x's and y's? What's that point in Cartesian? What is that point in Cartesian? What's the conversion? You're going to find this simple. What's the Cartesian? X is what? R cosine theta, y is r sine theta. So what's 4 cosine of pi over 6? What's 4 times the square root of 3 over 2? 2 root 3. What's 4 sine of pi over 6? What's 4 times a half? There it is. I just put it back in x's and y's. So plot that point. You're in the same point, right? You need not to plot x and y coordinates. Go over 2 square root of 3, go up 2. It's the same point as this point. Polar coordinates is huge. It is so beneficial in Calc 3 when you're dealing with the circles. That sphere you're talking about makes it real easy to deal with spheres, the way you project them and stuff, because you get these circle projections like on an XY plane. Cylinders, paraboloids, circular paraboloids. Before I do equations, can you convert backwards? I'll probably help me out. And when there's x, there's y. That's a simple port in Cartesian. You know where 1, 1 is? Where is it? First quadrant, go 1, 1. Can you get me back to, could you put that in polar coordinates for me? What would be that same point in polar? Well, what's the conversion? This has to be an r and this has to be a theta. So now I'm kind of lost because I was using this before. Which ones do you want to use? How do you think I can get r? Just look through them all.
The inverse tan?
That'll get you theta. Which one will give me r though? This one, Pythagorean theorem. That wouldn't do it. What's 1 squared plus 1 squared?
1.
1 squared plus 1 squared is 2, and then you'd have to take the square root of that, right? So it's 1 squared plus 1 squared equals r squared. R squared equals 2. R would equal plus or minus a what? Square root of 2. Now I said plus or minus. So I'm going to use the plus because what quadrant is that in? Yeah, that's in the first quadrant. So I'm just going to go r radius of square root of 2. Cool. Now how do I get this? I heard you. You said use what? Inverse tan of, what's the y and the x? Anybody know that angle? Very good. They're in the angle that makes that ratio for the tangent, 1/1 ratio. Now a 45-degree angle, pi over 4. I know some of them, they give you a bunch of practice problems in the book if you want to do them all. If you really like this stuff. But just be careful with that. Hey, now on to equations. And when I want you to convert equations, I need you to remember this. So if I give you something in Cartesian, I need you to just substitute these, okay? Let me give you a couple of those. First of all, I do want to point out, this is a very, very simple equation in polar coordinates. You know what that is? I hope you find that real. This is where you can really see why polar is very helpful with circles. R equals 3. If you put your calculator in polar mode and hit R equals 3, guess what it makes? It makes a circle because every point will be how far from the pole? 3 away. What does that form? A circle. That would be a circle with radius 3. By the way, you can explore this with your calculator. Just hit mode, hit polar, and try it. R equals 3. It's going to give an R equals automatically. Just radius of 3. So that's too easy. Hey, what would this be? Now I'm trying to trip you up, but you could simply take one of both sides. Square root of both sides, right? Look at this Cartesian. What would that be? What's r squared? You see the difference? X squared plus y squared equals 9, but the radius is a 9. What's the radius? 3. This is also a circle. Because one of the problems in the book did r squared equals 5 that I put for practice. Let me give you a tough one. In the directions, you ready? I need you, this is in 10.3. Polar coordinates. I know you'll get it. I need you to convert this, this is like number 25. X squared plus y squared equals 5x. In the directions, find a polar equation of the curve, represented by the Cartesian equation. And can you find a polar curve represented by the Cartesian equation? Let's find a polar equation of the curve. Represented by the Cartesian equation. Cartesian x and y, they also call it rectangular coordinates. Cartesian x and y, well, you gotta find a polar equation. What do you simply do? Who's got something great for the left side? Because I don't feel like jamming that into the x and jamming that into the y. You want to get everything in r's and thetas. You can leave constants though. What can I make x squared plus y squared? R squared, leave the 5. What can I put in place of x? Excellent. Not cosine theta, but don't miss that r on a test. You follow me? Be careful. Right? X isn't equal to cosine theta. X is equal to r cosine theta. Very good. Now I'm done, but can I simplify that? Can I simplify that? Yeah. I mean, what's on both sides? Now it's like I shouldn't like just divide it out because I could lose something. I could say r is equal to 5 cosine theta. If I factor, and r could also equal 0. But I'm not gonna write the r equals 0 because it's included here. Do you all agree there's an angle cosine where r equals 0? Does that make sense? I could have factored this. I'm gonna show you something. I could have factored. It's a lot of work, but what could I have factored out of this? R, and then I'd have this, right? So I really have two equations. What's one of them? R could equal 0. What's the other one? R equals 5 times cosine theta, right? Does someone see this? But isn't R equal to 0 included here? So I don't have to write the R equals 0. Here's my answer. Now look at it carefully. I removed an R here and an R here because I was factoring. But I'm not rewriting that because that's included here. There's a value of theta where R equals 0. I don't have to write that. It'd be superfluous. How about that? If I included the R equals 0. You could. It'd just be superfluous. There's the equation. Was that okay with that? By the way, does anybody know what this makes in Cartesian? That's a circle. Okay.
So it doesn't matter if it's theta included in the equation to equal 1?
Say again?
It doesn't matter if there's a theta in
Oh, you
R?
bet. Because what's the two? You have to go to a polar curve, an equation of a curve represented by, find a polar equation, and what's the two variables for polar? R's and thetas. You can leave any constants, but everything's got to be in R's and thetas. We can't leave any X's or Y's around.
But having a theta in R along with theta for the other part will be effective?
That's right, because every function here, R is a function of theta. That's what we're saying. And you got your graphing calculator. When you put it in polar mode, it's going to write as R as a function of theta. So hey, with Y's, remember, Y was a function of X. Now R is a function of theta. But what if you didn't see a theta, like the last problem, I had like R equals 3. And you go, oh, well that's just the radius of what? 3, it makes a circle.
Yeah.
By the way, this makes a circle too. It's just shifted. Does anyone notice that? That's just a circle that shifted a little bit. Cool. Hey, we're now going to do a problem like number, we're going to do two problems. These won't take long at all. The first one is R equal to 2 sine 3 theta. We're going to sketch this.
What number is this line?
This one is like number 35. All right. So I'm going to sketch this curve. R equal to 3, 2 sine 3 theta. R equals 2 sine 3 theta. Now if you want to investigate this already with your calculators, it's totally fine. You put it in polar mode, you're going to notice you get all these petals. And if you want to zoom it, just hit zoom trig. If you want to hit the zoom trig, it gives you a nice image of these petals. But we're going to do this by hand. So now I'm just going to make a table. When I make this table, I mean I have X's and Y's, but now I have thetas and what?
R's.
Thetas and R's. Now usually, because before I go by pi over 2, pi, 2 pi over 2, or 2 pi, and when you notice that's a 3 theta, so we got to go back to trigonometry. I think it helps if I look at what values of theta I could use in trigonometry. Do you know the period got affected by this? It'd be 2 pi over 3 would be the period of that thing in Cartesian. So I'm thinking, everyone, just think this, I'll write it way over here. If I was in Cartesian, and I thought of this as what? Theta, and this is R. What would this graph do? Just like in Calc 1, it went down, came up, but the period's not 2 pi, it was what? 2 pi over 3, what was this? Pi over 3. How high did it get? How low did it get? It got up to 2, and how low did it get? But I do want to point out, Owen, this is not a sketch of the polar curve. We're going to sketch the polar curve. That means you're going to sketch it in polar coordinates. This is just a representation in Cartesian coordinates. So I'll put that down, and that's why I put this way far away. This is not the answer. But this relationship is going to help us make this graph. Okay? So I do want to point out, what do they call this? This is graphing a relationship in Cartesian coordinates. So I'm going to put that here. This is a graph representing the relationship in Cartesian coordinates. Okay. And this is a graph representing the relationship in Cartesian coordinates. Well, can you help me plot some key points then? What's going on with, let's just think data was 0. What was R? 0, but how about, I'm going to use, and what would this be? What would be that point right there? It'd be a helpful point to use. What's half of pi over 3? Pi over 6. So everyone, in this scenario here, notice I'm going back to like a Calc 1 course. Every increment was pi over 6. I'm going to use this to help me come up with those values. Pi over 6, that's 2 pi over 6. This is 3 pi over 6. What's 3 pi over 6 reduced?
Over 2.
Over 2. And that's 4 pi over 6. Well, I'm now going to plot some points here. And we're going to make the curve. The key is you want to be able to make the one petal. So, pi over 6, pi over 3, what were some other cool points?
Pi over 2.
Pi over 2, and what was the last one? These are just good points to plot because of the nature of this expression. That's it. But I think this will help me. Now, what's sine of 3 times pi over 6? That's sine of 1, that's a 1, which 1 times 2 is what? 2. What's 3 times pi over 3? Pi, what's that? 0. Now, I want to make a note. And look what happened. Put this in your notes. From 0, 0 to pi over 3, this thing returned to a 0. The r value. What is r again? Distance from the pole. That's going to form one petal. So let's draw that one petal right there. We're going to sketch the polar curve. Well, can you just help me start out by sketching that first petal? It started, what was going on at 0? R equals 0 is 0 from the pole. Then what happened when it hit an angle like pi over 6? That's 30 degrees. And an angle of pi over 6, I'll just lightly put just a dashed line here. What did this thing do? It swung out a distance how far? Distance of 2, the curve, and then it returned at pi over 3 back to what? And I'm going to draw an arrow. Would you put an arrow on there to indicate the direction that it was traveling as t increased? See that little petal it made? That was just one petal. This will continue to make more petals. Right? Here, what's going on there? -2. And what would that be? 0. Now, can you help? I was wondering if you could help me plot this. Where is that point going to be? Pi over 2 is here, but the r is what? Negative. So you know where this petal is? It gets down here, doesn't it? Does everyone see where that point is? There's pi over 2. Look, here's pi over 2. This is 0, that's pi. It will be down here. So this petal would form by going down here, a distance of what? 2. But then it'll swing back to the origin. Now,